All right, so this video is 4.1c, and we're talking a little bit about how antiderivatives can be actually useful, maybe a little bit about what that plus c means, and we're going to get right into some vertical motion problems. Hopefully, before you watch this video, you have familiarized yourself with page 287, numbers 37 to 43, odd. What that is doing is it's asking you to take something like, let's say, y prime is equal to 2x. And it's saying that, like, let's say we have the point 2, 3, and they want you to find y. So if you're taking something like this is a derivative. You can antiderive it, right? So you can get that y is equal to x squared plus c. And then you can take this x and put it here, and this y and put it here, and find the c. And you'll get what's called they call this right here in the blue a general solution with the plus c in it. It's called a general solution to a differential equation. A differential equation is an equation that contains a derivative, and you can kind of see that this is containing a derivative, right? So that's a differential equation. The general solution is the blue thing, and the particular solution is when you actually do out the work and you get y is equal to, well, we don't know what the c is yet, but let's see. If we took that, it would be 4, and then there would be 3, so I think that it would be -1. Ignore the plus -1, it's just, that's the particular solution, okay? So just some terminology. The blue one is the general solution. It's generally the right thing, but it's not for this exact point, for this exact equation. And the red one's the particular solution. All right, so let's move on and kind of use this in actual, like, real life problem type of thing. Because you know you're always going outside and throwing the ball up in the air and measuring how fast it's going. So this will help you next time you go out and do that. So a ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Okay, let's put that into mathematical terms. So we have velocity of 64. So I'm going to say that, well, that's initial velocity. I'm going to say the velocity at time 0 is equal to 64. And they also say that it's from an initial height of 80 feet. So it's from an initial height of 80 feet. An initial height of 80 feet. So I'm going to say the position S at 0 is 80. So that's like a little bit of what we're trying to go with. And let's just try to take a second and think about that. What we really need to do is work backwards all the way from acceleration. So I'm gonna kind of erase this right now. We might use it later. But I'm going to actually write down what the acceleration is due to gravity. So we know that the acceleration due to gravity, we just know that the acceleration due to gravity is negative 32 feet per second. So because we know that the acceleration due to gravity is negative 32, we know that the double derivative of position is negative 32. And we know that that gravity doesn't change. It's always pulling at the same rate. So we can say that that's the function. It's a constant function. It has no variable. And now we're in better shape because we can actually antiderive this right here to get s prime of t. In general, that's why it has a variable in it. And that's negative 32t plus some constant. Okay, so you see the red. The derivative of position and velocity are the same thing. So those red equations are kind of representing the same thing. So we can now use the x and the y, or the t and the velocity, whatever you want to think of it, to get the general solution of this red problem. So let me show you what I'm doing. I'm taking this and plugging it in for t. I'm taking this and plugging it in for the velocity. So 64 is the velocity. That's equal to negative 32 times the time is 0 plus a constant. So the constant is 64. So I guess what I can say now is I know the velocity function, like, entirely. I know that the velocity is equal to negative 32t plus the constant, which was 64 in this case. So plus 64. So I want to note that saying v of t is the same exact thing as saying s prime of t. These are the same thing. I can write either of those. So we now have the velocity. We still don't have the position. That's what they're looking for. So we have to take this to another level. The good news is now that we're repeating the process, it won't be that bad. We just need to antiderive this red box. So the velocity, when it's antiderived, becomes position. So now we know that the position at time t, right, is equal to, and that's equal to, let's see, if we antiderive this, we'd have this as negative 16t squared plus 64t plus c. Hopefully that's comfortable for you, antideriving the red to get the green. We have some green information there, which says that when the time is 0, the position is 80. So if we kind of do that in our heads, we can kind of see if we plug in a 0 there, the constant's just going to be 80. Do you see what I'm saying? So you don't actually have to do this out necessarily, because they gave you initial position, and actually according to the equation, the initial position is always just added to the end. So this can be plus 80. Of course, you can do the math out to get there too if you want. But if you plug in 0, you'll get c equals 80, and you'll plug 80 in. So we finally got the answer for A. The position, s, as a function of time t. Wonderful. When does the ball hit the ground? So maybe you could pause the video here and try to think about what you need to do to find out when the ball hits the ground. I will tell you that if they're asking for when, then it's t equals question mark. So you're definitely trying to find t when something's happening. So think about that, pause, and we'll talk about it in a minute. Yeah. So if you know what to do, just go ahead and do it. If you need a little bit of a hint here, the ball is going to hit the ground when the position is 0. The position is s of t, so you really need to just set s of t equal to 0 and find time. So that was kind of a spoiler, but hopefully that's not a problem, that algebra. So set the position to 0, that's when it's going to hit the ground, and solve for t. All right, so once you've got the answers to that, I will tell you what they are. So remember, pause the video, give this a try, and hopefully you come up with t equals -1 and t equals 5. But like logically, could the ball have hit the ground a second before you even threw it? No, that doesn't make any sense. So we will throw that out, and we'll say 5 seconds. And that's accurate, like everything's accurate. The speed of gravity, or like the pull of gravity, everything that we've done there is correct. So in that actual situation, it really would take 5 seconds if you weren't paying attention to wind resistance, which of course does have a small factor. But if you're throwing a ball, it doesn't really have as much of a factor. If you're throwing a paper airplane, maybe more. So there's that problem. So let's kind of continue on, because, you know, we want to get it done here. Okay, friends, turns out this problem is horrible, and I don't think you should be trying this, honestly, right now. I mean, I'm going to give you 99% of what you need to do, then you do the rest, okay? Cool. So what I did was I kind of like underlined everything and put it into some mathematical like understanding. Those are the important things. I'm calling the initial velocity k, because we're going to use c later on, and ground level means that the position is 0. So that's all good. Now what I want to do is I want to start with this acceleration as -32, and I want to work backwards, just like you would with those book problems. And I get this equation. I get -32t plus that initial velocity, because when t is 0, you'll just have k, right? This is what this is. So this is the initial velocity. Now at that point, I need to do something special. I put a star there for this reason. I need to go down here, and this is the key to the whole problem. If you don't have this right here, you're going to be in some trouble. You're going to be at a maximum when the velocity is 0. When an object goes up and then stops and then comes back down, its velocity is 0 at the very top of that arc. So really, I'm setting this velocity to 0 and finding t. So when is this thing at a max? When time is k over 32. No, that's not a number, but that is when the object's at a max. Once we find our k, we'll know when that object's at a max. So I just set the velocity to 0 and solve for t, because otherwise we're going to have too many variables going on here, And when we have like 70 equations like this, maybe that's an exaggeration, but when we have a lot of equations, we can use those equations against each other. It's kind of like a systems of equations in a way. So now I'm going to continue on with normal life. So I'm going to kind of cover this up for a second just so you can kind of be aware. We're just forgetting about that for a minute, and we're going to keep antideriving. So we antiderive to here, which makes sense. We add a c. We don't want the k and the c to be the same number, so I made them different letters. We know that the initial position is 0, so I'm replacing that with 0. And now we're finally going to use that stuff over here. Notice the blue stars. They should all line up. Plug in for the time that variabilized answer, and you'll get an equation that should be solvable. And you want to know when the object's at a height of 555, so the position needs to be 555. So if you solve this equation here on the bottom right of the screen, you should be able to get there. Give it a go, and we'll call it from there. So I guess that's long enough for this video. I will see you in the next one. Peace.